Now I will present a sample proof of triangle congruence using these three pairs of congruent parts. Please repeat the same process for the other two pairs of congruent triangles. So let's prove triangle congruence for the purple pair. Alright, so for the purple pair here, this one. Congruent pair number 1. Side BD is congruent to side BD. So we have congruent sides, and the reason is reflexive property. So side BD is equal to side BD. It's equal to itself. Next, congruent pair number 2. Angle GBD is congruent to angle FBD. Congruent angles. Reason, the angle bisector BE divides the vertex angle into two equal parts. So we have the angle bisector BE or BD. So it divides vertex angle into two equal parts. So we can say then that angle GBD is equal to angle FBD. Next, congruent pair number 3. Angle BFD is congruent to angle BGD. We have congruent angles. The reason, side FD is perpendicular to side BF by construction. So let me show you. So we have side FD is perpendicular with side BF. Hence, triangle GBD is congruent with triangle FBD. And the reason is the side angle postulate. Therefore, we can conclude that side GD, this side GD here, is equal or congruent with side DF. Why? Because of the reason. Therefore, we can conclude that side GD is equal to side DF. And the reason is CPCTC. Corresponding parts of congruent triangles are congruent. Furthermore, after showing congruence for the purple pair, lemon pair, and orange pair of triangles, we can state the important equality that side GD is equal to side DF, and side GD and side DF is also equal to side DE. The objective of this part of the proof is to logically show that after the angle bisectors were constructed and formed the incenter D, and after connecting such point of concurrency D to the sides of the triangle at the shortest distance, it formed line segments perpendicular to the said sides. Such perpendicular lines from the point of concurrency are equal. This can also be further illustrated by drawing the incircle. Again, we just have to show that line GD or side GD is equal to side DF and is equal to side DE. Lines GD, DF, and DE are the radii of the incircle. So here's our first figure. The incenter D produces equal line segments GD, DF, and DE that are perpendicular to the sides of the triangles at the points of contact between the incircle and the sides, where the sides serve as tangents to the incircle. Finally, we are going to prove and demonstrate the congruence of the same pairs of triangles by proving that the two pairs of corresponding vertex angles are congruent. So the two pairs of corresponding vertex angles are the pair of corresponding parts that will be. Finally, we're going to prove and demonstrate the congruence of the same pairs of triangles by proving that the two pairs of corresponding vertex angles are congruent, serving as the pair of corresponding parts with missing and unknown congruence. So at this part of the proof, we have to show that the two pairs of corresponding vertex angles are congruent. Alright, so the congruence of the two pairs of corresponding vertex angles are missing. It's not part of the given. So, right, so let's prove now triangle congruence for the purple pair. So congruent pair number 1, again we have side BD is congruent with side BD. Okay, reflexive property. Then congruent pair number 2, side GF is equal to side DF, right? Because side GD and side DF are radii of the incircle as proven in step number 2. Then finally, congruent pair number 3, side GB is equal to side FB. Alright, so we have congruent sides. And we're going to make use of the Pythagorean theorem for our reason. So the Pythagorean theorem formula, c squared is equal to a squared plus b squared, is the distance formula for lines of right triangles. So we're going to have some algebraic manipulation here. Side GB is equal to the square root of the square of side DB plus the square of side GD. Okay, and side FB is equal to the square root of the square of side BD plus the square of side DF. Okay, and then we can do substitution. Alright, so we're going to substitute DF with GD. Okay, because we know that GD and DF are equal based on congruent as a pair. So we have side GB is, we don't know the side GB, it's missing. Okay, for example, it's missing. So we are going to find the square root of the square of side BD. So BD plus the square of side GD. Right, so again, side GB is missing, it's not given, and yet side BD is given and side GD is given. So we're going to square side BD, we're going to square side GD, get a sum of the two squares, and then get the square root. So we have this equation. Side GB is equal to square root of the square root. So we have this equation. Side GB is equal to square root of the square of side DB plus the square of side GD. And also, side FB is missing, it's not given. And then also side BF or side FD, also side BF or side FB is missing, yet side DF is given, and then side BD is given. So we're going to square FD, square BD, get a sum, and get a square root. So we have the second equation here. FB is equal to the square root of the square of side BD plus the square of side DF. And now we all know that side GD is equal to side DF as stated or proven here at section B. So we can do substitution now. We're going to replace side DF with side GD. So we can say that side FB is equal to square root of the square of side BD plus the square of side GD. Okay, and now we are going to do another. Now have a look at equation 1 and equation 3, or the first line and the third line here. Okay, so we have the same right side. So we can therefore say that side JB is equal to this expression and this expression is also equal to FB. Okay, because at the first line and the third line, we have the same right side. So, considering transitive property of equality, then we can say that side JB is equal to side FB. Okay. Now we have proven congruency to 3 pairs of corresponding sides. So we can then say that triangle GBD is indeed equal to triangle FBD, and the reason is, of course, the side postulate. And since these two triangles are congruent, then all of the corresponding parts are also congruent. Therefore, we can say that angle GBD is also equal to angle FBD. So these are the two angles at the vertex. Hence, we have proven and shown that the incenter produces equal line segments that are perpendicular to the sides of the triangle at the points of contact between the incircle and the sides, where the sides serve as the tangent of the incircle. Now, such equal line segments produce two congruent triangles with a common side, which is the angle bisector. And those line segments, hence we have proven and shown that the incenter produces equal line segments that are perpendicular to the sides of the triangle at the points of contact between the incircle and the sides, where the sides of the triangle serves as the tangents of the incircle. Also, we have shown that the equal line segments produce two congruent triangles with a common side, which is the angle bisector. And this angle bisector bisects the vertex angle of the triangle into two equal parts. Right? So because of that incenter, we have able to prove, okay, that with the angle bisector, we can have two vertex angles that are equal to each other. Okay, so indeed, that angle bisector is such equal line segments produces two congruent triangles with a common side, which is the angle bisector. And we have proven that indeed that angle bisector really bisects the vertex angle of the triangle into two equal parts. Here's now our conclusion. The point of concurrency of angle bisectors is the incenter. From the incenter, equal short distances extend to the sides of the triangles, forming the radii of the incircle. And the incenter is the point of concurrency as it connects to the vertices and bisects the vertex angles into two equal parts, constructing angle bisectors.